The frequency distributions are strong with this one, using Markov chains to create a phrase generator for Star Wars characters by Jonathan Goodson. Authoring a movie script naturally requires writing character dialogue that is in alignment with the phrases that a character says. Dialogue that is inconsistent with a character's established vernacular norms comes across as unauthentic and low quality, harming the quality of the movie in the process. This project is an attempt to investigate how well an implementation of the Markov model will serve in producing a character phrase generator based on known movie character dialogue. Markov's property states that the future state of a sequential process is exclusively indicative of its present state, and nothing else, certainly not past states. In this research experiment, we attempt to invoke this idea by considering a character statement or sentence as a sequence process. Each word is influenced solely by the word that preceded it. To get an informed perspective of the trends by which a character words tend to follow each other, we will create a language model based on all of the statements that every Star Wars character has made. With this information, we can then begin attempting to manufacture statements that linguistically align with a character. The strategy to accomplish this aspiration can be thought of as having two main parts. Number one, parse known character dialogue to create a character's word sequence frequency distribution model. And two, leverage this model to generate a character's sayings. Using Markov chains and freely available movie script data from Kaggle, I sought out to parse and ingest movie script data from characters to create a word mapping distribution that will be used to generate statements that are in alignment with a movie character's vocabulary and speech style. The data that is ingested is quite simplistic. A previous Kaggle researcher has already parsed the scripts of Star Wars Episodes 4, 5, and 6 into delimited files with 3 fields per line: line number, character, and character dialogue. Here is the template that the output of this portion of the project aims to produce. Once we have our model, then we put it to work. In our simulation, we start with a random word that a character has started a sentence with. Then we leverage our previously created frequency distribution as the probability basis for a randomly selected next word. The word that follows the new word is determined the same way, and the next word, until a logical sentence end is reached. A key concept here is that each next word selected is not selected at complete random, but rather is selected based on a weighted probability calculated from our frequency distribution. The creation of the language model went well. Shown here is an example excerpt of the token distribution of a character that was leveraged to generate character sayings. Each item within the character node is a word that a character said, and the items within are a distribution of words that directly followed the initial word, along with the number of occurrences that the initial word was followed. According to the distribution shown here, Yoda followed the word "the" with the word "force" 14 total times. Character phrase generation succeeded, to an extent. Specifically with the character Yoda, the phrases generated by this model routinely resembled Yoda's unique vernacular style. The outcome of this endeavor was oftentimes delightfully amusing, but hardly romantic. It could certainly stand some improvements. One example is how Markov chains, fueled solely by sequence frequency, are indifferent to grammatical accuracy. For instance, the noun force is used ad nauseum in Star Wars to describe the ubiquitous energy that binds together all the living things of this story's fictional universe. However, force is also a relatively common verb as well, which the Markov property simply is not designed to grasp. This occurrence has been a noticeable drawback, in that our model does not fully appreciate the tense and context of the present token, and create something obviously wrong, oftentimes more than once, further compounding the confusion. Successive versions of this solution would seek to address language tendencies like this using techniques like advanced language model APIs.